so it's a very high multiple of an ample line bundle, for example, then it's well known that if you embed any variety by a sufficiently positive linear series, what you get is always projectively normal. So the H1 of all twists of the ideal sheaf vanish. So X is projectively normal. So this is well known, i.e. all the H1 of the ideal sheaf is for all M. Okay, so you don't have to worry about H1. And then we're back in this situation that I mentioned last time, where the higher cohomology of the ideal sheaf is just determined by the cohomology of the structure sheaf. So then if, so then if I is bigger than 2, we've said this kind of implicitly last time, then the HI, how do I want to do this? The HI on projective space of a twist of the ideal sheaf, let me write this as M minus I, because that's what we need for regularity. This is just the same thing as HI minus 1 on X of OX, M minus I minus 1. I'm sorry, M minus I. The twist isn't changing. So we're down, to compute these cohomology groups, we're down to a cohomology of some, intrinsically some line bundle on X, and just since we're embedding by a complete linear series, this is just HI minus 1. Remember, we're embedding by a line bundle L, so on X of L tensor M minus I. So we only need to understand when these groups vanish, and this is kind of clear. So let's take I equals n plus 1. So the point is that if L is sufficiently positive, then this group will vanish just by Sayre vanishing, provided that the exponent is positive. So we only need to see how big M needs to be to get a positive exponent. And the sort of borderline case is we take I equals n plus 1, and then what we need is Hn on X of L to the M minus n minus 1 equals 0. Okay, so when does this vanish? So first of all, this expression here had better be non-negative. And if M equals n plus 1, then this will vanish if and only if Hn of X, OX is 0, which means we're in the situation where PG equals 0. Otherwise, we need M at least n plus 2. So, okay, so that's that. Okay, so so what's the moral of this? So the moral of this is that if you want to fix a variety and look at a very positive embedding of that variety defined by a complete linear series, you're not going to get anything particularly interesting looking at regularity. So the interesting, now, but remember, what is regularity? Regularity means if you look at the whole resolution of the ideal sheaf, it bounds the kind of most negative twist you get. So the really interesting question is not to study, so the interesting question is to study the individual pieces of the resolution of the ideal sheaf, is to then study the individual pieces terms in the resolution of the ideal of X. Let's say the homogeneous ideal of X in PR. And so this is where the syzygy questions come in. So in other words, you don't, just by looking at regularity, you don't get any interesting variation from variety to variety. But if you look at the individual pieces, you'll see that there's a very, that's kind of where the interesting picture arises. So I now want to sort of introduce, so these are the syzygies. So I now want to introduce some notation and vocabulary, which gets a little bit heavy, I'm afraid, but it's unavoidable, about syzygies. Okay, maybe I'll go to a new board right away. Okay. Okay, so let's introduce some setup. So first of all, let me see how I'm doing here. No, okay. Okay, so what's the setup? Okay, so let's introduce some notation. So here's the setup. Okay, so we have X, some variety embedded in projective space of sections of L. And again, we can think of this as PR. So R is the projective dimension of L. And again, we're always looking at complete linear series. And then let's let S be the symmetric algebra on H naught of L. So this is the homogeneous coordinate ring of the projective space we're embedding X in. And then we want to look at the graded ring associated to L. So R will be R of L. So this is the direct sum for all M of H naught of ML. So this is, of course, a graded ring, but we're only going to be concerned with its module structure. So this is a module over S. So this is a finitely generated graded S module. So we're not, so we'll only be concerned with it as a module. Okay, and so like any finitely generated module over a polynomial ring, it has a minimal graded free resolution. So we want to consider the minimal graded free resolution, minimal graded free resolution so I'll call it E dot or E dot of X and L, depends on L, of R over S. Okay, so let's write this out. Now, the professionals actually go from left to right, so their maps go from right to left. And I always find it hard, but right before just earlier this morning, I decided I'm going to try to do this. So we'll see if I can get this to work. Okay, so we start here. So here's our module. And so we want to start, so this is a module over the polynomial ring. So we want to start by picking generators. Well, so in degree 0, this has a canonical generator, right? Because in degree 0, you have the constant function. So let's put that in. We have one generator in degree 0, and then we'll get maybe some other generators in higher degrees. So I'll write this minus A0J. Okay, now we map those onto R. There's a kernel. We take generators of the kernel, so I'll call this what? Direct sum of S minus A1J and so on. And we keep going. So, okay. S minus 8, maybe I won't put those in. So you keep going. You have some generators of those second module of syzygies and so on. And you keep going until you get to the end. And now how long does the resolution last? So it always ends by the R step. But it might end sooner. It might, or the length of the resolution is either R or in between R and R minus n. If the thing's Cohen-Macaulay, then it's R minus n. But anyway, since in practice R is going to be much bigger than. Is n dimension of x? Yeah, I'm sorry. N is the dimension of x. Thank you. Right. So, but anyway, it's essentially, you should think of it as essentially ending after R steps. Okay.
What you mean by minimal?
So okay, yeah. So minimal means you don't have any you don't introduce any generators and then kill them with relations. So one way of saying, so each of these maps is given by a matrix of homogeneous polynomials. And minimal means that there are no non-zero constants in the matrix. So I mean, you don't introduce a generator and then a relation that says the generator is 0. So you do it kind of efficiently. And then it's a theorem that the numerics here are independent of the choices. I mean, this will become clear in a minute. Okay, so let's call this the 0 piece. This is the degree 1 piece, and so on. This will be the ER piece.
Why is E0 not just S?
Because so let me make a remark. E0 is S if and only if it's projectively normal. So I'm not assuming that L is terribly positive now. So what does it mean? So remark. So that's a good point. So remark. First of all, what does it mean if and only if L is, X is, this embedding is projectively normal? Because what is it, let's think what it means for E0 to be S. That means that all the higher sections of higher powers of L come from taking homogeneous polynomials in the degree 1 generators. So that's equivalent to being projectively normal. So if L is sufficiently positive, that's automatic. But it's for the setup here, it's a better thing to look at like this than to assume that to begin with. Say it again? No, that's not true. So you have to be careful. If you think of this as a sheaf, I want all the maps to be surjective on global sections. So if you sheafify, you see, and you didn't have it projectively normal, it would end a little bit later. Yeah, I really want to take it like this. I really want to make sure I get all the sections of powers of x. Yeah. OK, so it's E0 is S. And in this case, this is a good point. In this case, so what's really interesting, of course, is to understand the equations defining the ideal. And in this case, the resolution from this point on determines resolution of the ideal. And so in this case, if it's projectively normal, we have, so then if it's projectively normal, then we just get S. So the kernel of the first map is just the ideal of x. And what we have is a resolution of the ideal. Have a resolution of the ideal. So this is going to be the most interesting case. But the theory works better if you don't, as you'll see, if you don't assume to begin with that it's projectively normal. But in all the applications, it will be. OK, good. So and then what else? What can we say about the degrees here? So I claim the second remark is that all the aij's, so all the all the a0j's are bigger than or equal to 2. And then the other ones, all for p bigger than or equal to 1, all the apj's are bigger than or equal to p plus 1. So why is this? So this is a reflection of the fact that we've got a complete linear series. So we're assuming that R in degree 1, R is just h naught of L. And we're assuming that we've embedded by a complete linear series. So the degree 1 stuff is accounted for by the homogeneous polynomials. But we might, if it's not projectively normal, we might need some new generators in degree 2. And so this, and then why is E1, why are all the generators here of degree at least 2, where we're assuming, that it's embedded in a non-degenerate fashion. So a degree 1 generator here would be essentially a linear space containing x, and we're assuming it's not contained in linear spaces. So, so these are the kind of evident constraints. So let me do, I'm sure everybody's seen this, but let's just do the two baby examples that you can kind of do easily by hand, just so we do something concrete. OK, so I was over-optimistic here. Okay. Okay, so. OK, so let's do two baby examples so we can see what's going on. So I think I mentioned these the other day, but it's good to actually see them. So let's do two examples. So let's do the twisted cubic curve in P3. So C equal P1 and P3, twisted cubic. OK, so the rational normal curve in P3. OK, so how do we find the syzygies of this? Well, there's this classical fact that, so we'll call the variables here T0, T1, T2, T3. So there's this classical fact that you can describe the twisted cubics determinantally. So you look at the following matrix. Sorry, it's the locus where. So So I want to look at the following matrix. I take a matrix T0, T1, T2, and then T1, T2, T3. So these are my homogeneous coordinates in P3. And I look at where the rank of this matrix is less than or equal to 1. That's a classical fact that this is describes the rational normal curve. Okay, so this means that C is the ideal of C is generated by, so C, this is of course projectively normal. So the R0, the E0 piece is just R. So this means that this ideal of C in PR in P3 is generated by 3 quadrics, namely the two minors, so generated by 3 quadrics, and I'm going to index them by the sort of, so delta 0, 2 will be T0, T2 minus T1 squared. Delta 0, 3 will be T0, T3 minus T1, T2, I guess. And then delta, what do I have? 1, 3 will be T1, T3, okay, minus T2 squared. So this is, of course, classical that these generate the ideal. Okay, but now the interesting thing is how do we get relations among these? So here's the classical thing you do. So what you do is you take this matrix and you double a row. So let's, for example, double the top row. So we look at the matrix T0, T1, T2, T1, T2, T3, and then let's double the top row. So I'm just going to write the top row again. Okay. Now, it's pretty clear that the determinant of this matrix vanishes, right? So this is something we're fond of telling our, okay. So this matrix vanishes. The determinant of this matrix vanishes, but now what we can do is we can expand along the bottom row and we get a relation among the delta ij's whose coefficients have degree 1. So this says that T2 times delta 0, 2 minus T1 times delta 0, 3 plus T0 times delta 1, 3 is 0. Okay, so this is a syzygy among the delta ij's whose coefficients, a weight 1 syzygy, whose coefficients have degree 1. And similarly, if we doubled the second row, we would get what? We would get, let's see, T3 times delta 0, 2 minus T2, I guess, times delta 0, 3 plus T1 times delta 1, 3, if I've done my numbers right, or 0. And this, as it turns out, these generate all the syzygies. So what does the resolution look like? So what happens here is, so let me actually leave a little bit of room here. So what happens here is that, so we get this, well, we get the homogeneous coordinate ring. It's got one, it's projectively normal, so there's one generator. Then we have 3 quadratic defining equations, so this gives us 3 copies of S minus 2. So the map from this is given by a 3 by 1 matrix whose entries are just these quadrics. And then there are 2 degree 1 syzygies among the quadrics. And so this matrix here is given by basically this thing there. So each row of this matrix gives us a syzygy among the quadrics. Okay, so this is what the resolution of the twisted cubic looks like. Let's do one other baby example, which is in some sense easier. Let's do the elliptic quartic curve. So let's take E in P3, elliptic curve of degree 4. Okay, so I mean, this is again a famous thing. An elliptic curve of degree 4 is the complete intersection of 2 quadrics, as is well known. So E is, again, it's projectively normal. E is the complete intersection of 2 quadrics. And so now the resolution is just the Cazul resolution of a complete intersection. So now where we get, let me put it down here, is we get, so R is the homogeneous coordinate of E. Again, it's projectively normal. But now we have 2 quadratic generators. And now the only relation among these quadrics is the one Cazul relation. So we get something like that. Okay, so that's, I mean, obviously these are baby examples, but these are, I mean, you can do, I mean, of course, it's hard to compute stuff by hand, but in low degrees, for low degree curves and P3, B4, you can kind of see what's happening. No, remember, the regularity, so the I mean, yeah, so the regularity is 2 for the, it's 2 for the elliptic curve, 3 for the complete intersection. Remember, the regularity depended on whether or not you get some top dimensional forms. So the elliptic curve has, I mean, the genus is, I mean, H naught of K is non-zero, right? Okay, so let's see. Okay, now if you remember in the first lecture, let me see how I want to do this here. Right, so in the first lecture I mentioned these classical theorems that say if you have a curve of degree 2g plus 1, it's projectively normal, 2g plus 2, its ideal is joined by quadrics. And so I explained that the way to generalize those to higher degrees was to, I mean, this was this idea of Mark Green's, is to ask when the first certain number of terms of the resolution are as simple as possible. So the question here, the first thing we want to talk about for the rest of the day is, so this was suggested by Green, so his question really is that the way to generalize these classical results is to ask when are the first k terms, so k syzygy modules, terms in E dot generated in lowest possible degree. So in other words, for the ideal, for the generators of the ideal to have lowest possible degree, that means they should be generated by quadrics. For the next term to have lowest possible degree means that the relation should be, among the quadrics should have degree 1 coefficients. So let me introduce a definition here. We'll say that this embedding line bundle satisfies property nk. Property nk. If what? So first of all, what we ask is that E0 should be S. So in other words, the embedding should be projectively normal. So this is when k is bigger or equal to 0. So we just build projective normality into the picture. And then for positive k, for positive things, we ask that and E sub p be just, everything have just degree p plus 1. So minus p minus 1 for less than or equal to p less than or equal to k. So this is the definition. So let's see what this means. Let me just draw a picture here and I'll write it out. So okay, so let's assume that it's projectively normal. So that means that the first term is just S. Okay, and then we ask when k is equal to 1, we ask that the E1 term, everything has degree 2. So this would be a direct sum of S minus 2s. So this is when, so this is E0, this is E1. So we're asking that everything in E1 have degree minus 2. So this is saying that it's generated, the ideal is generated by quadrics. Then the next case, we're asking that for E2, we're asking that everything be generated in degree 3. So what does this mean concretely? etc. So what this means concretely is that so i.e., so n0, as I've said, just means that L is normally generated. So the embedding, it defines a projectively normal embedding. N1, as we've just seen, so that means, first of all, it should be normally generated, because each of these kind of requires that the previous one holds. And then N1 would mean that this is just a bunch of S minus 2, so that means that the ideal is generated by quadrics. What would N2 mean? Well, again, that means we're asking that the ideal be generated by quadrics. But the new thing in N2 is that this should be a direct sum of S minus 3s. So that means that all the terms in this matrix, this should be a matrix of linear coefficients, L, I don't know, J alpha. So this should be a matrix of linear polynomials. And what that means concretely is that the relations among the quadrics should have degree 1 coefficient. So the syzygies among quadratic generators Q alpha in the ideal should be generated by relations with degree 1 coefficients, or spanned by relations of the form summation L alpha Q alpha equals 0. Okay, and so on. Where the degree of L alpha are 1. And so on. Okay, so what about our two examples? So, this is bad Blackboard technique, but permit me to do this. So our twisted cubic, so C in P3, twisted cubic, this satisfies N2. I mean, I guess in some sense you could say it satisfies N infinity, but we've seen that it's projectively normal, it's cut out by quadrics, and the relations among the quadrics have degree 1 coefficients. On the other hand, if we take this elliptic curve E in P3, the elliptic quartic, so what we saw there is the ideal is generated by quadrics, so it satisfies N1, but it doesn't satisfy N2 because the relation among the quadrics have degree 2 coefficients, not degree 1 coefficients. So this has less n's. And that's, as we'll see, because the elliptic quartic somehow is less positive than the twisted cubic. 4 is somehow smaller than 3 in this game. Okay. Yeah? Well, I mean, it was really Mark Green that kind of introduced the idea. I think he and I don't know. Yeah, I mean, sometimes it's called Green, or I think it was actually introduced, the actual vocabulary was introduced in a paper of him and me. But in any event, so the logic of this is that Mumford talked about normal generation and normal presentation. So normal generation is, we're calling N0, normal presentation is N1, so it seemed like N was a reasonable name to call it. But I think these have become pretty standard now, so I think everybody agrees on what these are called. Okay, so so what's the theorem? The first theorem I want to talk about later. So this will be this is kind of the first theorem in the subject. So this is Green's theorem. So it explains what's happening for curves. So let's consider C a curve of genus G. And L will be a line bundle of well, let's say a line bundle on C of degree D. Okay, so the theorem is that if the degree is bigger than 2G plus 1 plus K, then L satisfies this property NK. Okay, so let's see what the numbers say. So when K is equal to 0, this says a line bundle of degree 2G plus 1 defines a projectively normal embedding. If K equals 1, this says that a line bundle of degree at least 2G plus 2 defines an embedding in which the curve is cut out by quadrics. So those are the two classical cases. When K equals 2, it says if you have a line bundle of degree 2G plus 3, the relations among the quadrics are spanned by those with degree 1 coefficients and so on. So this was the kind of the first. And you can see then what's happening with the twisted cubic, which is G equals 0. So if G equals 0, K is 2. So this is saying that, it's best possible there. On the other hand, if you take this elliptic curve of degree 4, then G is 1, so 4 is 2 plus 1 plus 1. So then this theorem predicts that N1 holds, as it does, but there's no reason for N2 to hold, and it doesn't. So those are borderline cases for the theorem. Okay. So now I want to actually explain in some detail the proof, which uses kind of vector bundles. But the key idea for the proof is to interpret the syzygies as what are called Cazul cohomology groups. So interpret syzygies as Cazul cohomology groups. Okay, so let me now talk about Cazul cohomology. And okay, so okay. Okay, so I want to introduce unfortunately, the indexing is a little bit confusing, and there's nothing you can really do about that. So I want to introduce some vector spaces that are basically multiplicity modules that sort of count how many generators there are at a certain stage in the resolution in a certain degree. So here's the basic definition. So given, again, we're back to an arbitrary X embedded by a very ample line bundle L. So we'll define KPQ of X with respect to L. So, okay, here it is. It's the degree P plus Q minimal generators. So this is the minimal generators of the Pth module of syzygies of this ring R. And so this is a finite dimensional vector space, and things are rigged. So what we're really asking is that, so what we're really saying is that the Pth module of syzygies, so the EP, the Pth term in this resolution, so we're going to take a sum. So P is, the index P is telling us how far back we are from the front of the resolution. And then the Q term is telling us something about the degree. So we're taking the sum over old Q of KPQ, which is a finite dimensional vector space, times S minus P minus Q. Say it again? Oh, instead of just R? Yes, and we will introduce yet more. Yes, we'll do that on Thursday, right. So we'll have an extra layer of complexity, right. So, and now this, this funny shift to P plus Q may seem perverse, but in any event, you'll see in a minute that does turn out to be the right indexing. And, okay, just so, and then we'll write little kpq will be the dimension of big kpq. So it's a finite dimensional vector space. Okay, so let's do some examples. And then there's, so So let's take C and P3, the twisted cubic. Let's see, is the twisted cubic still on the board? Where? Is it? I don't, let me put it up again, because I don't. Yeah, so what it looked like R. We had we had S, then we had 3 quadratic generators and 2, so that's what it looked like. Okay, so what's happening here? So this is giving us a K00. Let me just do dimensions. So this is a generator, K00 is 1 in this case, because this is P equals 0. It's a generator of the ring, and it's in degree 0, and nothing else is there. So here we're we're at stage 1 of the resolution, so it's a K1, and it's weight 1. So we're going to call these things piece syzygies of weight Q. Sorry, I should have said that. I don't know. Okay, so this is 3. These have weight 1 because 1 plus 1 is we're at stage P plus Q is 2. And then these are second syzygies of weight 1 again, because 2 plus 1 is 3, and then there are all the other KPQs are 0. And then there are these things that people like to draw called Betti tables. So let me show you. This is, I've been sort of working on and off for syzygies for 30 years, and it's only like in the last year that I've made my peace with these tables, but I think it will be useful. So, I'm sorry, yeah. So there are going to be 3 different weights. So 0, well, we're not going to get any 2s in this case. So this is telling us down the vertical axis we have the weight of the syzygy, and here we have which syzygy we have. So this has 1 generator in degree 0, so we put the number here. And then people like to draw these little lines to say that it's 0, because otherwise your tables are filled up with 0, so you draw a little line instead. Okay, in weight 1, well, we don't have any other weight 0 syzygies. In weight 1, we get 3 generators here and nothing there. And here in weight 2, so here P is 2 but Q is 1, we get like this. So this is what's called the Betti table. Now the way you read these things is that since the horizontal axis measures where you are in the resolution, and so they're kind of maps. They're maps somehow going from the first syzygies to the 0th syzygies, second syzygies to first syzygies. And the way this works is that if you have a map that's given connecting 2 entries that are horizontal, it's given by linear forms. So the map from S minus 3, 2, so this is given by a 3 by 2 matrix of linear forms. But here, when you're going from here to here, it's given by quadrics, because it's 2 steps. You're not going horizontally, you're going 1 horizontally, 1 up. So you see, the thing is that when you map by linear, when the matrices in resolution have linear coefficients, you're staying on 1 row of these tables. And so this is why this is a good notation. What we'll see in general is that the number of rows of the tables tends to be bounded. So if we did an index like this, our tables would be going down, down, down. So this is a kind of, it's confusing, but this is a, okay. And what happens for these elliptic quartics? Well, I'll just quickly tell you. You can, while I'm erasing, you can see if you can practice by drawing the Betti table of an elliptic quartic. So, okay, so these tables are a little bit confusing, but in any event, once you make your peace with them, they contain all the essential numerical information of the resolution, the grading. Okay, so let's. So I'm going to go a little bit longer, and then we'll have a break. But I want to get to the kind of. I'm going to go maybe 5. Okay, and so, okay. And so, Fine. So now, yeah. So what does this property nk mean in terms of these? So what this property nk means, so for k equal to 1, this property nk means that that the k pq's are 0 for q not equal to 1, and p 1 bigger or equal to p, p bigger than 1 in between k. So what this nk means is that everything in the first p steps of the resolution, everything is linear. So that means you're all on the row, you're always on the kp1 row. So you're always, so this is, you get, you know what, I forgot to do the, I'm sorry, I forgot to do the elliptic. So let me quickly do the elliptic curve, what the Betty table looks like. So sorry, I forgot to do that. So here we have p, here we have q. So we have one thing here. We've got 2 quadratic generators, but now here we have 1 degree 2 relation. So the map from here to here has degree 2. So k, property nk means that after this p equals 0 stuff, everything is lying along the first row for k steps. Okay. Now, so what's the basic thing that lets you do anything with these things? So the basic fact is that there's a way to compute these things as Cazul cohomology groups. So the little proposition or the little theorem here is that kpq of L is the cohomology of a Cazul type complex. Cazul type complex, hence Cazul cohomology. So let me write this down. Okay, so so in the middle, it's going to be the cohomology at this spot. So I'm going to take wedge p h naught of L times h naught of QL. Okay. And then I'm going to write down a Cazul type map. So I'm going to peel off one of the wedge terms and throw it in here by multiplying. So it's going to be wedge p minus 1 h naught of L times h naught of q plus 1L. So I decrease the p's and I increase the q's. And this is going to receive a map from wedge p plus 1 h naught of L times h naught of q minus 1L. And the map is just what you might think it is. So I hope, I mean, if I take a wedge thing, S1 wedge SP, tensor some G here. So what I'm going to do is I'm going to peel off one of the S's and multiply it by G. So then I'm just going to go to the sum, I guess minus 1 to the I. So I take S1, I omit the ith term, and then I take this ith term and I multiply it. I multiply G by it. So I take each one by one, I take one of these off and I multiply by G, and then I alternate signs and I get a complex. And the cohomology of this complex is these Kp cubes. And this incidentally explains, I mean, when you think about it like this, the indexing is almost forced on you. So okay. So what's the proof of this? What's the idea of the proof? And then I want to reinterpret it geometrically, and then we'll take the break, and I'll quickly prove Green's theorem. So, okay, this is, if you think about it right, it's almost a tautology. So let's let C be the S mod S plus. So it's the residue field of homogeneous residue field of S. So I take polynomials mod polynomials of positive degree. Okay, and now I claim that since so this is almost obvious, since E dot is a minimal resolution, then I claim that this KPQ, what it is it's just tor P over S of this module R against C, and I take the degree P plus Q stuff. I claim that this is kind of obvious because how can you compute these tors? So what you do is we resolve R we resolve R like this. And these are sort of matrices of homogeneous polynomials. And when we tensor by C, we just set all the entries of the matrix 0. OK, so then what you're left with is some vector spaces here, some graded vector spaces with 0 maps between them. So this is so tensoring by C. So when you tensor by C sets, so you make entries of matrix, you set entries of matrix. Equal to 0. So if you just think of it like this, it's almost a tautology that that's what these KPQs are. On the other hand, you could also compute these tors by resolving. So we computed these tors by resolving R and tensoring by C. But we could just as well resolve C and tensor by R. But you can also compute these tors by resolving C and then tensoring by R. So how do you resolve C? Well, there's just the Cazul resolution. So you have just S here, and then you have H naught of L. That's S in degree 1 times S minus 1. Then you have wedge 2 H naught of L times S minus 2, and so on. So this is what it looks like when you just look at the S. This is the S resolution of C. It's just the universal Cazul resolution. OK, and so now what you do is you tensor by R, and you take homology, and then if you keep track of your grading, that's what you get. So then you get complex in the theorem. So what the theorem really comes down to is that you can compute, it's the commutativity of Tor. You can compute Tor by resolving either variable. OK, so let me have 2 more minutes, and then I'll explain. I want to explain sort of reinterpret this geometrically, and then after the break, we'll prove Green's theorem, and then see some other stuff. And then next time OK. So let me just quickly. OK, so now there's a little bit of geometry that comes into the picture. So far it's been kind of all algebra, but at some point there should be some geometry, and it enters here. Trying to think. Yeah, let me do it. Like this, yeah. OK, so now the point is that we can reinterpret these Cazul complexes in terms of an interesting vector bundle that lives on the curve, or on any varieties. So now I want to reinterpret geometrically. OK, so if I'm given this X and this very ample line bundle on X, what I want to do is I want to look at, I have an evaluation map. So we have an evaluation map of vector bundles. OK, so my evaluation map, I take the trivial vector bundle. I take the trivial vector bundle whose fibers are the space of sections of L. And then I can evaluate, I have an evaluation map that maps this to L, and as long as L is globally generated, this map is a surjective map of vector bundles. OK, and so the interesting gadget is going to be the kernel of this map. So let's define M or ML to be the kernel of this evaluation map. So let me put that in here. So we get an exact sequence like this. OK, so this is a vector bundle on X whose rank is the R of L. So this is a vector bundle on X whose rank is R of L. And it's in some sense a familiar object. So for example, if L defines a map like this, then what it is, you can also think of it, I mean, this is essentially the Euler sequence. So it's omega 1 PR, there's a twist, twisted by 1 restricted to X. But anyway, I can think of it like this. Okay, and so this is the basic exact sequence here. This defines this interesting bundle L. So let me call this star. And so the proposition here is that if we have some rather minor vanishing, so here's the proposition, is let's assume that, what do I want? Some hi of kl equals 0 for I positive and k. So this is, I mean, the kind of thing that's going to happen when L is very, reasonably positive. And so then for q greater than or equal to 2, I can compute these kpq's cohomologically. So we have that this kpq of x and L is equal to h1 of wedge p plus 1 of ml tensor L. So especially assuming that it's already projectively normal, nk holds if and only if, I'm sorry, this is L to the q minus 1. So if and only if nk holds, if and only if h1 of wedge p plus 1 of ml tensor L to the q minus 1 equals 0 for positive. So q. Okay. So showing this property nk is reduced to some vanishing, checking some vanishing involving these vector bundles. And let me just quickly, so the point is I can take wedge products of this sequence and splice it together, and then I get a complex. Well, let me do this here. So what we do is we take wedge products of this sequence star and we splice. So let me put this up, and then we'll take our break. Oh, well, too late. Okay, I should have kept that up. But anyway, what can we do? Okay, so let's see what we get here. So if we start taking wedge products of that thing and splicing, we end up with a. I'm sorry to write all these long diagrams here, but I think so. Okay, I'm going to get a wedge p plus 1 h naught of L tensor L to the q minus 1. Then I'm going to get wedge p h naught of L tensor L to the q. And I'm going to get wedge p minus 1. So these tensor L to the q minus 1. So this is an exact sequence of vector bundles. And the point is that these, if I take, so here I get wedge p of ml tensor L to the q. So these are wedge products of this sequence, and I'm kind of splicing them together. So here I'm going to get wedge p minus 1 ml tensor L to the, sorry, this is q plus 1, and so on. So I just, so this is now an exact sequence of vector bundles. Okay? Now, the Cazul cohomology is just I take H0 and I take the cohomology of that. That's my Cazul cohomology. So KPQ is just the cohomology of H0 of middle row. And then I just break it up into short exact sequence involving these m's, and you can compute. And so now chase the diagram. Okay, so that's the picture. So the point is that these m's, these are actually very interesting bundles. I'll say a word about that later. and they control the syzygy. So this is all rather general, and then after the break, we'll prove Green's theorem by actually computing one of these H naughts on a curve. Okay, so that's the, sorry to go over it, but we'll do Green's theorem. Okay. So it's a break. Now we have our.